All right, now we want to do similar things that we just did with RIP, but we want to do it for OSPF. So the first thing we're going to do is get rid of RIP. So we'll go ahead and get rid of RIP and add OSPF at the exact same time. So we'll do no router RIP, gets rid of router RIP, and then we want to add OSPF router OSPF. One's what do they call it? Process ID. You can have multiple OSPF processes for different types of service, but we're not going to talk about that. And then for OSPF, you need to give it a network statement. Network. Cool thing about OSPF is you can specify a network address and then a wildcard mask. A network address and a wildcard mask, and then it will enable it on all IP addresses that match that network address and wildcard mask. In this case, we put 255.255 at the end, which essentially means I don't really care what's in the last 2 octets. So basically, this is going to make it work for any interface that has an IP address that starts with 192.168. We'll talk more about wildcard masks when we talk about ACLs later on, access control lists. But for now, just type what I have. And then we need to tell it an area. And area 0 is the backbone area. So if we don't have any other areas, we need to make this one area 0. You can configure multiple areas, and it does a lot of load balancing. Not load balancing. Yeah, I'm not talking about that. You can configure multiple areas to reduce the amount of computation required by the routers. How about that? I'll say that. So that was really the command we needed to enable it. So now we're going to go do the same thing on the other routers. No router RIP router OSPF 1 network 192.168.0.0.0.0.255.255 area 0. So that should be that one. No router RIP router OSPF 1 network 192.168.0.0.0.0.255.255 area 0. Yeah. And then one more router. No router RIP router OSPF 1 network 192.168.0.0.0.0.255.255 area 0. So that should be it. So hopefully we learned things and it shows up, hey, I just learned some stuff. So we'll go back over to our table 1 and look. So this guy says, hey, I learned from 21.1. Or maybe that's my interface. Basically, the guy got some routes. Do show IP route. So if we look at this routing table, a couple things we want to notice. The letter change. Now we have an O out there for OSPF, right? We have our network, our same network. That's pretty stupid. That's going across a serial link. OSPF is supposed to be better than that. I don't know why that's there. Hopefully we'll get an update from somewhere else in a minute, and that will start going across the one of the faster links. Okay, there we go. Whew. Like, stupid OSPF, what's your problem? So if we look at our line, we have O. The line looks very similar to RIP. We still have this time here for our last update. We have the interface we're going across. If we notice this, our administrative distance is 110 instead of 120 for RIP, which means that OSPF is a better routing protocol. And our metric is 4. So I'm not exactly sure what that metric means. It's a cost metric that gets calculated based on the speed of the interface. But basically, you should just know that the lower the number, the better, and slower links cost more. So here was when it was on the serial, the metric was 65, and our fast Ethernet link has 4 to get over to the other network. So right now, we don't know our full path. We know it's going to go from here up to this router. So we look at this router. If we look at this router, you would expect maybe it would go across the gig link, but you never know. So basically, if we look at this, we're going across. We have two routes with the cost of 3, and it's going across either link. with doing load balancing like before. So there we go. That's the route we should be taking up to this router and then using either of those links. Let's confirm that with a trace route. So there we go. Trace route up to 11.1, 11.253, 21.2, which is that's the fast Ethernet link. And this one went across the gig link. So it's doing the same thing RIP was doing when we had the serial interface out. So that's good. OSPF's using the faster link. Why is it not using the gig link exclusively? Well, maybe, I'm not real sure. Maybe it's smart enough to know that down here is fast Ethernet anyway, so it doesn't matter if it goes faster across the gig. I'll have to look into that, but I think that's probably what it is. Maybe it's smart enough to know that this is not gig down here, so it doesn't really matter which way it goes. So now what we're going to do, we're going to cause a failure. We're going to shut down the FA01 interfaces because that's what we did last time and cause it to do something different. Start a continuous ping. We'll shut down the FA01 interfaces. FA01 down. FA01 down. Oh, not 01, stupid. That was the wrong interface. 1 and 1, 0. I mean 0, 0. 0, 1 was the, yeah. Let me turn those guys back on. Make sure my ping's still working. Hey, the ping went down when I shut the interfaces down. All right, it's back. So now I'll go shut down the right interfaces. Sorry about that. 0, 0. 0, 0. And let's look at our ping. If we look at our ping, hey, you look at that. It doesn't even look like we missed a ping. So if we go look at our routing table, that's not a very good routing table. All right, that's not a very good routing table. Let's look at this routing table because this is the one we're going through. All right, so we look at this routing table. It failed over to the serial interface, and that was probably my fault for failing the FA00 so quickly that it wasn't able to take over yet. In a second, everything should be back to normal, and it should be back to this interface, that path. Let's hope for the best. All right, so there we go. So now we're using the gig interface on this router, and hopefully this router has learned what it should have learned. So now it's going across the fast Ethernet back up to that other router. So that's what should have happened when we took this down. So basically with the failure, when this link came out, it pretty quickly should have failed over to this link, but I screwed things up by not waiting for things to stabilize after I broke that other link. So you should test that the proper way and make sure you get the expected results. So now we saw that it actually used a serial when it was down, so we know that's going to work. So I'm not going to test that. I'm going to bring this FA01 back up, FA00 back up. So that was the failure of the interface. The router knew the interface was down, so it could immediately take action, right? So now we're going to do the other kind of failure once we wait for the routing table to stabilize, and we will know it's stabilized when we have both routes back. All right. We don't have both routes back yet. We still only have the gig route, so we'll wait a minute or two until that happens. Have those both back up? Yeah, those are both back up. All right, there we go. I learned the route from the other router, so they should be both back up. So that took about, what? There we go. Now they're both back up. That took about 2 minutes for that to come back up. So I don't know if that's 2 minutes. Maybe you should add a timer to figure out how long it took to come back up. But the thing is, while it was coming back up, we still had the good route, so we didn't lose any pings. So now we're going to cause the other kind of failure where we break it in the middle and see what happens. So you should start a timer if you have a timer. We're going to break that, and we're going to see what happens to our pings. So we dropped one. Look at our routing table. The route's still in there. The bad route's still in there, and apparently it's still trying to use it. So we got a ping. So this is behaving similarly to the way RIP behaved. But remember, RIP took like 3 minutes for it to recover. So let's see how long it takes OSPF. Oh, hey, something just happened. The dead timer expired. Interface is down. So if we look now, it's still in there, which is odd. I bet it's gone now. So it's gone now. So that was a lot faster than RIP. That was what, maybe 30 seconds if you had a timer going, I don't know. So there's a dead timer that helps OSPF decide sooner if things are down or not. And now I'm going to go ahead and bring this link back up. We'll see what happens when the link comes back up. Shouldn't have any impact on the traffic. We're doing spanning tree over here, so 45 seconds. Or so, maybe it's 50 seconds, I can't remember. I think it's 25 and 25, no, 15 and 15 and 20. Yeah, I don't know. I should know that. So let's see if that's what we're supposed to do on the lab sheet. Oh, if you're in the lab, you're going to run the throughput tester before and after failure. Yeah. All right. All right, so let's see if that's back. All right, it says it's back, loaded to full. We have both routes back. Let's go look at our ping. And we didn't drop any ping. So that was kind of fast. After the failure, it took like, I don't know, 30 seconds or less, whereas RIP took like 3 minutes. So OSPF's better than RIP. OSPF's using the faster links, so that's better than RIP. So that was it for the OSPF part. The next video, we will disable OSPF and use EIGRP.